How do you fly a car-sized, nuclear-powered drone through the freezing skies of an alien moon? We're learning more about Dragonfly this week on Planetary Radio. I'm Sarah El-Ahmed of the Planetary Society, with more of the human adventure across our solar system and beyond. Imagine a 1,000-kilogram drone soaring through a thick atmosphere over organic sand dunes. That's the vision for NASA's Dragonfly mission, which is currently being built and tested for an epic journey to Saturn's largest moon. This week, we're exploring the engineering required to fly a craft of that size in Titan's frigid temperatures. Joining me from the Johns Hopkins Applied Physics Laboratory are lead rotor engineer Felipe Ruiz and principal investigator Zibi Turtle. They'll reveal how the mission currently stands in its integration and test phase, and how they upgraded the rotor design to get the smoothest ride through the Titanian skies. Then Bruce Betts, our chief scientist, joins me for What's Up, where we look back at the Ingenuity Mars helicopter, the first powered, controlled flight on another world. If you love Planetary Radio and want to stay informed about the latest space discoveries, make sure you hit that subscribe button on your favorite podcasting platform. By subscribing, you'll never miss an episode filled with new and awe-inspiring ways to know the cosmos and our place within it. Titan is one of the most Earth-like worlds in our solar system, despite being frozen and covered in methane rain, rivers, and lakes instead of water. But its thick atmosphere and low gravity make it a perfect place to fly. It's about 40 times easier to fly there than it is here on Earth. That's why NASA chose a rotorcraft to explore it instead of a traditional rover. Dragonfly will be able to hop from site to site, covering ground that no wheeled rover could ever reach. It's going to be sampling the organic chemistry of this world that mirrors what early Earth looked like before life ever took hold. To walk us through how this all works, I'm joined by two guests from the Johns Hopkins Applied Physics Laboratory, which manages the mission for NASA alongside a massive team of partner institutions and universities. Dr. Elizabeth Turtle, who goes by Zibi, is the principal investigator on Dragonfly and a planetary scientist whose career spans Galileo, Cassini, the Lunar Reconnaissance Orbiter, and Europa Clipper. She's a returning guest and always a joy to have on the show. And Felipe Ruiz is Dragonfly's lead rotor engineer and a senior staff mechanical engineer at APL. He's also worked on the Double Asteroid Redirection Test, or the DART mission, and the Parker Solar Probe. Felipe is a longtime fan of Planetary Radio, so it's a real thrill to finally have him on. Here's my conversation with Zibi Turtle and Felipe Ruiz. Hey, thanks for joining me.
Thanks, Sarah. Glad to be here.
Thanks, Sarah. Great to be here.
It's been a while since we had an occasion to talk about Dragonfly on the show, and we're coming up. There's been a lot of developments recently, so I'm really glad to have you both on. But for people who aren't familiar with the spacecraft, Zibi, can you tell us just generally, what is Dragonfly? Why are we going to Titan?
Dragonfly is a mission to send a rotorcraft, a large rotorcraft, about the same size as the Curiosity or Perseverance rovers on Mars, to Saturn's moon Titan. The moon Titan has a dense atmosphere and lower gravity than Earth, makes it the perfect place in the solar system to fly. And that allows us, while exploring Titan, to be able to get to a variety of places on the surface. And that's what we really ultimately want to do. Titan is a very carbon-rich place. The complexity of the molecules on Titan is similar to the complexity we think we would have had on the early Earth. And what we really want to study is the kinds of molecules that are being produced there, and whether they're like the kinds of molecules we think would have been produced on the early Earth before life developed. Titan's basically been doing complex prebiotic chemistry experiments, the chemistry that occurred before biology, for an extended period of time, and the results are sitting on the surface. And so Dragonfly is designed to go there to study the compositions of those materials and see what's there.
I mean, other than trying to blast off from the moon with some kind of, Apollo module or something, there's only ever been one other powered flight on another world, which is the Ingenuity helicopter on Mars. But this is like a much better situation for flying, I feel, with the thick atmosphere and everything that's just waiting there for us. So I'm really excited about this, but we still have about 2 years out from launch. So where does the mission currently stand in terms of like integration and testing?
Yeah. In terms of flight on Titan, it's about 40 times easier to fly on Titan than it is here on Earth. So Titan is doing a lot of the work for us, which is really excellent. At this point, coming up on 2 years to launch, the team is incredibly busy in our integration and test phase. So here at APL, people are, every day working on building the electronics, building the lander itself, and assembling all of that together and doing testing of the hardware. The instruments will be coming in, will be being delivered during the next several months, and those will be installed also on the lander. And then in parallel with the lander build here at APL, Lockheed Martin, out in Colorado, is building the entry vehicle, the heat shield and the back shell that will protect Dragonfly as we descend down into Titan's atmosphere, as well as the cruise stage that takes us from Earth to Titan. So all of those components are coming together in parallel, and our partners are working right now to build the instruments. So so it's a very, very busy time.
It's a really complex thing, and I don't think the scale of this thing really resonated with me clearly until very recently. It was about 2 months ago. I was at an event in Washington, D.C., and someone from APL was there with VR headsets. I got to experience the size of Dragonfly through that VR headset, and I tell you, it's literally taller than me. I had to look it up afterwards. So it's just wild how big this is and how complex this machine is. How many people does it take to build something like Dragonfly? Like you've mentioned, there are many institutions, but how many people?
Yeah, all of these missions are, incredible team efforts. And on Dragonfly, right now, there are probably a few thousand people across the country and around the world working to bring this to reality.
That's amazing. Everyone's going to be so excited when it's finally flying on another world.
Yes.
When I first saw this thing, I initially called it like a quadcopter. It looked to me like it had, 4 rotor sets, but it's actually 8 rotors on this thing. And Felipe, you're deeply involved in designing this. This has been like your brainchild for a while. What drove that design decision to have 8 rotors on this spacecraft?
Yeah. Hey, Sarah. So that's an excellent question. And it is a way of balancing requirements between getting the furthest range and having the most efficient vehicle that can fly on Titan against being able to fit in the aeroshell. And so we have to be able to get the lander to Titan when we launch. We launch inside of an aeroshell that has the sheet shield, the parachute cone, and the systems we need to descend. And so that gives us a diameter that the whole rotorcraft has to fit within. And if you do the study, it actually ends up being that within that aeroshell diameter, a 4-rotor system maximizes rotor area. In maximizing rotor area, you become most efficient with the power that's actually required to fly. And then we stack 2 rotors on each arm to further maximize rotor area, further maximize thrust. That allows us not only to have the control margins we need, generate the thrust we need to fly, but also be the most efficient that we can within those parameters that we're given.
If only we could origami this thing up the way we did with JWST, right? We get 1 million rotors on this thing.
And we actually went through some trade studies where we had deployable rotors and mechanisms, and you'll see that the rotors are a single monolithic piece of aluminum, because we'll talk about the cryogenic aspect of Titan. Titan is terribly cold. And so one of the trades we made was it's better perhaps not to have mechanisms that have to work after so many years of cruise at a cryogenic temperature. Better to have rigid rotors, and there's some savings and complexity there.
Yeah, I mean, it is really, really cold, but it also doesn't have the temperature swings that some other worlds, like, say, Mars, would have. How does that change the way you're designing this spacecraft that is going to be operating at these super cold temperatures?
So it is terribly cold. We're far away enough that the day-night cycle on Titan actually does not change the surface temperature a bunch. Surface temperature is about minus 180 C, minus 292 F. It's roughly the same as liquid nitrogen. And so from an engineering point of view, it's been a huge challenge just to keep the internal of the vehicle warm enough, the avionics and the batteries especially, so that we can survive. The key way we do that is that the vehicle has a MMRTG, it's nuclear powered, and we use the heat that comes out of that RTG. We have a system of fans and ducts that circulates the air inside the vehicle around, and that allows us to keep everything warm enough at Titan to make sure all of the components survive. if you actually look at a picture of Dragonfly and you see the outer mold line is primarily a foam, and it is insulative. And we have some very, very tight heat leak requirements because it does not take a big heat leak to overcome the heat that the RTG is producing, the heat that we're producing internally through the avionics. And so that has been one of the biggest challenges ever since we really started developing the lander. We've had some pretty unique test campaigns and unique test facilities that we've built at APL to replicate the Titan environment. And we then have to test through different operating cadences because, as you can imagine, flying is a very power-intense activity, so it's a heat-intense activity, whereas hibernating at night is not. So there's unique features like a cold duct and a hot duct. There's a valve on the lander that can circle air closer to the skin of the lander, closer to that cold environment of Titan before it brings it back in, which lets us fine-tune some of those temperatures on the surface.
How do you keep the rotors rotating? Like, how do you prevent the motors themselves from freezing?
So we don't. We let the motors freeze. And that was an early decision that we made because the amount of power it takes to keep the motors from freezing was more power than we had to give, more power that we get out of the RTG and more than we can pull out of the batteries. And so we have a motor design that is designed and analyzed and built to freeze. We warm those motors up in the EDL sequence before first flight and make sure they're at temperature before we release from the aeroshell. And then for subsequent flights, there's actually a whole pre-flight procedure, of which a big step is bringing those motors up to temperature with internal heaters such that they're ready to fly. And then between flights, they are frozen in essentially the temperature of Titan.
That's some wild engineering. But, you mentioned this earlier, that it's a lot easier to fly on Titan than it might be on Earth, right? Because of the density of the atmosphere. How does that atmospheric density actually change the rotor design or the shape of the blades?
Right. So the density is about 4 times that of Earth's density. If you look at all of your aerodynamics equation, essentially scales loads. And so for a rotor that spins at the same rotation rate on Titan as Earth, we generate 4 times the thrust. So that helps us be much more power efficient. And that's where the number that Zibi said earlier comes from, right? It takes a lot less power between the denser atmosphere and the 1/7 gravity to fly on Earth than it is on Titan. We also care about a couple other things in the Titan atmosphere that are beyond the density. We care about the viscosity. We care about the speed of sound. We typically don't want rotor tips that go supersonic. It leads to high drags, high torques, and high vibrations. And then viscosity for us means drag. So we take all of those, and compared to an Earth analog, the Dragonfly rotors operate in an aerodynamic regime that is more akin to what you see in a wind turbine on Earth, as opposed to what you see on Titan. And so the Dragonfly rotors, the airfoils that we selected, the blade pitch distribution is all designed and mined for that operating regime.
I'd ask you how heavy this spacecraft is, but we'd be thinking about that in terms of Earth gravity. So instead, I guess I'll ask, how much mass is in this spacecraft, and how hard is it to actually get it off the ground on Titan, even if it's easier to fly there?
Yeah, so the maximum mass that we are using in our rotor design and our flight design is just shy of 1,000 kilograms, so about 2,200 pounds. That is, for a sense to scale, a Robinson R-44 helicopter weighs roughly that much. Divide that by 7, and you get to roughly a little bit over 300 pounds. Now we're talking in terms of thrust, so in newtons, about 400 newtons. And to put that in scale, that's about what a Vespa scooter weighs on Earth. And so you get that help from the gravity. We can spin rotors up to 1,250 RPM. Each rotor pair, for reference, generates about 800 newtons, so about 200 pounds. Add all that up together, and the whole system at max RPM can generate about 3,000 newtons, so just shy of 800 pounds. And so, hey, that number is bigger than what we see the way the lander is going to be on Titan. Great. And in fact, we will typically not spin the rotors that fast. That is a max RPM that we use mostly for controllability. So it lets us trim out the vehicle. It lets us get acceptable margins for our pitch, roll, and yaw controllability. And then there's also a sticky ground constraint that, as we learn more about Titans, if you can talk about this, we have some margin where we say, hey, maybe we land in a place that's got sand dunes and it's not that easy to get off the ground. It's a little bit stuck. And so that thrust to weight margin lets us fly and have conservatism in the design and high confidence that we can fly through all the flight regimes we want and throughout the whole flight envelope.
Part of why I know that these rotors are going to be super successful is because the company Sikorsky is involved in this. And they're the ones that build these Black Hawk helicopters, right? What does their rotor expertise bring to a mission like this? And what have you been learning from their team?
So much. So Sikorsky has over 100 years of lessons learned and expertise and really institutional knowledge that we can leverage for a mission like Dragonfly. We brought them on when we started getting into the implementation and production phase of the lander. And they've been instrumental to help us with all of the analysis that it takes, not just looking at the rotor and making sure it's going to survive the flight environment, but what are the loads? What is the flight envelope? What sorts of things and aerodynamic regimes like vortex ring state that we have to fly through during EDL do we need to be extra careful of, and where should we spend extra resources to make sure both in the analyses and the testing and the verification, we do the due diligence to make sure that any issues that we might discover, we discover here on Earth. They're helping us with hardware. We have a cryogenic rotor fatigue test coming up here in about a month where we're going to build ourselves a little chamber, take 4 rotors down to Titan temperatures and cycle them with hydraulic cylinders so they break. And Sikorsky has been running tests like that for decades. So there's a lot of institutional knowledge that we're taking, for example, just for that small scale test. And then even moving forward, making sure all the flight hardware gets verified adequately. We had them in our clean room about a week ago. We did something called a ground vibration test. And the ground vibration test is you take the fuselage, you hang it off a crane with bungees. So it's like a free condition as if it's flying. And then you hit it with a modal hammer and stingers to shake it like the rotors are going to shake it so you understand the structural dynamics. And that's a test they do all the time. That's a test that was novel for us on the APL side, but having that expertise and having the folks that do that for a living and, get good test data that we can then use to correlate our models and build the confidence we need to then fly on Titan is unique. And then in addition to Sikorsky, I want to give some credit to the Penn State Vertical Lift Research Center of Excellence. So before Sikorsky got involved, especially in the conceptual phase and proposal preliminary design, we actually worked with Penn State's aerospace department and that Lift Research Center of Excellence to work the proposal, to do the early design on the rotors, to do the early design of the aerodynamics and aerodynamics analyses. We wouldn't be here 2 years away from launch if it weren't for them. They were critical in the initial design, and they're still a huge part of the team.
There is so much that I wouldn't have thought goes into figuring out every single contingency. What would you say are the biggest aerodynamic challenges that you're trying to overcome when you're trying to solve for a place like Titan?
So I'll give you a couple examples. If you look at early images of Dragonfly, you will note that the lander has rotors with 2 blades. And if you look at more recent pictures of Dragonfly, you'll note that we now have a lander with rotors that have 3 blades. So when we put the proposal together and when we did the initial rotor design, we had 2-blade rotors because that let us put the rotors out as far from the lander CG as possible while still staying within the aeroshell. And what that means is we have longer arms, longer control arms for the torques that we then use to fly the lander. So it helps with the control margins. The drawback to that is 2-blade rotors, through a quirk of dynamics, aerodynamics, and some of the harmonics that happen when you go through forward flight, shake really hard, really, really hard. Early on, the decision was we would rather focus on maximizing control margins, and we can probably deal with the vibration issue. Turns out, did enough analysis, enough testing to realize we can't deal with the vibration issue. We're probably going to fatigue or endurance fail something that we need to change the rotors. And so we upgraded the rotor design to 3-blade to mitigate that vibration issue. So that's been one of the biggest changes. That change happened after our first wind tunnel test. So the second wind tunnel test, we had redesigned rotors ready in time, and they performed actually quite well compared to what we used to have. So we're very happy with that. The other big challenge I'll talk about is scaling. And so there's very unique test facilities that NASA has, specifically the Transonic Dynamics Tunnel at NASA Langley, that get us close to Titan's aerodynamic conditions, but it's not perfect. And so the rotor design, we picked airfoils and we picked the plan form that is not the most efficient design for Titan, but it is a design that through the different Reynolds numbers that the rotors operate both in the wind tunnel and then at Titan, and then the Mach tip numbers, we can correlate from that wind tunnel test analytically to what we see on Titan with high confidence. And how do we pick the most efficient airflow? How do we pick the most efficient landform and twist distribution and tip geometry? We don't have that confidence because that is a rotor that is very much built for the Titan environment and for nothing else. And so there were some trades to be made to say we need to make sure that our test program, our analysis program, the software that we use to analyze is robust enough through the conditions that we can actually test on Earth and build that confidence to fly on Titan. And we're going to take a little bit of a hit in efficiency to do so, but without that confidence to fly, we're not willing to launch.
Yeah, which just means we have to do a lot of testing. And in order to do that, you need a bunch of different test models. And I was lucky enough to see one of them. It was about a year and a half ago. We did a live show in Washington, D.C., and the team from APL brought this it was like a smaller scale model of the Dragonfly spacecraft. How many different models do you have, and what are they all designed to test?
So you saw what we call the integrated test platform. The integrated test platform is what we do Earth flight test in. So that is a model that actually flies. And a scale model that is primarily used for testing and development of some of our flight-like software and algorithms with hardware in the loop. So we can take some of the things that we program and fly in the closed loop sims and fly them on Earth and see how they behave on Earth. There's a couple other models. We've had 2 big wind tunnel test campaigns and 2 different models for that. So the one that's near and dear to my heart is the full-scale model that we built. We flew that in NASA Langley's Transonic Dynamics Tunnel. It's a semi-span model. So what that means is it's only half of the vehicle. So if you imagine running Dragonfly through a bandsaw, and so it's only 2 arms sticking out in half the fuselage, that's what the model looks like. Stick it up on a wall, and then be in full scale. That test lets us go through more of aeromechanics testing than we would have otherwise been able to. And so that means loads, that means stresses, that means putting the rotor in the vehicle through actually a couple lifetimes and worse flying conditions that we would expect on Titan. And from a structural mechanical point of view, that helps us build confidence that it can survive. We had a second wind tunnel test model. We actually flew that in the Transonic Dynamics Tunnel 2, and that was a partial scale model, but it was a full span model. And so that actually looks like the full lander, 4 arms, 8 rotors. And whereas the previous model, we could only really actuate the model in pitch, so we could move the nose up and down. That full span model lets us roll it, lets us pitch it, lets us yaw it. And so we can put it in different angles of attack, different flight regimes, and really understand how the aerodynamics of the body are going to interact with all of the rotor spinning through the different aspects of the flight envelope. And then getting away from aerodynamics and our mechanics, we mentioned how thermal is such a challenge for this mission. And so there is a 4th full-scale model at APL that we call the DTM, the demonstration thermal model. And that has been used for thermal testing. So at APL, we have a Titan chamber. It's a 16-foot cube in test section. It can go down to that minus 180 C liquid nitrogen like temperature. And we have been using that as a high fidelity model to prove out our thermal design, prove out our temperature control techniques, prove out that the insulation we've picked on the process to install it not only works, but is robust, and work through some operations on Titan that then help us correlate not only our thermal models, but also our computational fluid dynamics models, because Titan is convection driven. And so unlike a spacecraft where you care mostly about radiation, we have convection. And convection takes a lot more testing and analysis to make sure that all the models are right and that we know how to operate the vehicle on Titan and keep everything within thermal limits.
You also did heat shield testing recently in New Mexico, right? What has that kind of revealed about how this vehicle is going to handle actually entering Titan's atmosphere?
Sure. There's a Sandia test facility, the solar tower, and it has a lot of mirrors, and they focus the heat, or they focus the light from the sun into a single very small point. And the team, engineers at NASA Ames, one of our partners from Lockheed as well, was out there at the solar tower test facility where they can take a piece of the material that is used on our heat shield to protect Dragonfly as we go down through Titan's atmosphere and subject it to very high temperatures to make sure that the material behaves as expected and will indeed protect Dragonfly when we get to Titan. So that testing completed earlier this year, and happily it was very successful and demonstrated the robustness of the entry material.
That's a really cool way to test that. It's like the most extreme end of like putting a leaf under a magnifying glass under the sun.
Yes, but scaled up quite a lot.
Mm-hmm. You mentioned earlier the Titan chamber. This is kind of a space designed to help us test the environment on Titan. But what specific elements of Titan's environment are we testing in that chamber? Because we can't get everything perfectly Titan accurate.
Right. And that's one of the big stories of Dragonfly, where there is not the perfect test facility to do everything we would like to do on the vehicle. And so we break out testing into different facilities, be they wind tunnels, be them environmental chambers, be them thermal test equipment chambers. Two main Titan simulators. We have what we call the TPEC, the Titan Pressure Environment Chamber. It's 5 feet in diameter, 5 feet deep. And the two key parameters that we match there are temperature, so that gets us down to minus 180 C, and pressure. Titan surface pressure is about 1.4 times Earth's. That matters a lot for convection and making sure that the heat transfer that we get convectively actually matches what we would expect to see on the lander. The full-scale Titan chamber is a little bit different. It is 16 feet by 16 feet by 16 feet, so it is a big cube. It also gets us down to minus 180 C, and that is primarily used for full-scale testing. So the DTM that we talked about, the full-scale thermal model, gets tested in there. In a couple short months, the full-up lander will get tested in there, and we actually do 2 Titan test campaigns, one before we go to Lockheed and one after. And that matches the minus 180 C condition. It doesn't match pressure. We run that chamber at just under a Earth atmosphere. But then with the knowledge that we have from the TPEC, we are able to correlate the results we're going to get out of that Titan chamber test to what we would expect to see on Titan. And so both of those add up to essentially the thermal correlations and validations that we need.
We'll be right back with the rest of my interview with Felipe Ruiz and Zibi Turtle after this short break.
Hello, I'm George Takei, and as you know, I'm very proud of my association with Star Trek. Star Trek was a show that looked to the future with optimism, boldly going where no one had gone before. I want you to know about a very special organization called the Planetary Society. They are working to make the future that Star Trek represents a reality. When you become a member of the Planetary Society, you join their mission to increase discoveries in our solar system, to elevate the search for life outside our planet, and decrease the risk of Earth being hit by an asteroid. Co-founded by Carl Sagan, the Planetary Society exists for those who believe in space exploration to take action together. So join the Planetary Society and boldly go together to build our future.
You also did some rotor testing at Langley, I believe. And if I read correctly, it was like you used Freon to simulate Titan's atmosphere. How close of an analog is that exactly?
The Transonic Dynamics Tunnel is a unique facility in the world. The entire facility is the size of a city block.
Whoa.
And the test section is 16 feet by 16 feet. So you go up to the 3rd floor of this facility before you walk into the test section. The entire tunnel is a pressure vessel, so it can run in air, but then the facility can also be brought down a vacuum, and then they backfill it with a heavy gas, Freon. It's R134A, so it's a environmentally sensitive version of Freon. What that does is it lets us scale some key parameters to Titan that we otherwise would not be able to with Earth-like testing. So the density of the atmosphere, we get about 80% of the way there with that R134A as we get to Titan. So it helps a lot with dynamic pressures. But even more importantly than that, from an aerodynamics point of view, it lets us match key parameters like thrust coefficients, advance ratios, tip Mach numbers, Lock numbers. And while we don't exactly match Reynolds numbers, we're close enough that we can scale that performance in a way that we're only scaling across a very small range as opposed to trying to go from Earth-like 1 atmosphere conditions all the way to Titan. And so we take all of that information, we plug it into all of the aerodynamics and mechanics models that we have to correlate. And then we take those models, we flip the switch, turn it to Titan, and that's how we get our expected flight conditions.
But luckily, too, you're not subject to solar panels or things like that, like they are on Mars, or that day-night cycle that is pretty similar to what's happening on Earth. So your team's not going to be on Mars time, thankfully. But how long is a day on Titan, and how does that change your operational rhythm?
A Titan day is 16 Earth days long. So you're right, nobody's going to be living on Titan time. It actually means that we can do operations during the day here on Earth and kind of tailor that during the Titan day. So there's about a week of operations during the Titan day, and most of the ground in the loop activities where we're communicating back and forth with the lander and sending up new commands and getting data back. Well, we can actually schedule that during during business hours. So that makes it somewhat easier on the team. I expect it's actually going to be hard for people to, while Dragonfly is operating during the Titan day, to actually go sleep. And I expect that there will be a bit of a challenge to make sure everyone is taking care of themselves and that we're taking, shifts and things like that. But the primary operations can actually be scheduled during the business day here on Earth, which will make it a lot easier from that perspective.
I know functionally the spacecraft itself can fly at nighttime, but are you going to be flying during the Titan night, considering how difficult it'll be to actually see where you're going?
Yeah, we do terrain relative navigation, and we want to be communicating with Dragonfly before and after the flights. So all of the flights will be during the Titan day and during the Earth day, or the Earth day here at Mission Operations. But we can do some activities at night. Some of the instruments will be monitoring Titan conditions, atmospheric conditions, listening for Titan quakes, Titan earthquakes. And those will operate all the time. And if there is a Titan quake, we'll take, a quick set of data. So there are activities we can do with a science payload at night. The camera actually has a set of LEDs at different wavelengths, and some of those wavelengths are in the ultraviolet, where organic materials can fluoresce. And so there could be kind of a spooky camera observation during the Titan night where we illuminate the surface with the ultraviolet LEDs and see if we see fluorescence from the organics. A few different activities over the Titan night.
We don't have any orbital assets around Titan, which means we can't communicate back to Earth during the Titan night, because as we are on the surface that faces away from the sun, it's also facing away from the Earth. And so those ground in the loop activities, well, since we can't communicate to Earth, we keep them during the day when we can get downlinks from DSN.
But you mentioned this earlier, that the entire thing is powered by an RTG. How long can it actually fly before it needs to kind of sit back down and settle in to do some science?
Right. So Dragonfly is powered by an MMRTG. The flight times and the different flights we take can vary based on ground in the loop. So we have reposition and hops, which are anywhere from under 10 meters to 100 meters. That is our safe landing circle that the vehicle evaluates when it's flying as a 10-meter radius. And so a reposition just says, hey, we're going to jump from one spot to the other. Or a hop is about 100-meter radius. So that's someplace that we've managed before, and we have a high confidence we're going to find a landing site. We have other different flights like scout to land, jumps, committed jumps. The longest flights are on the order of about 30 minutes. And that's all when we're on the surface. EDL and first flight is different. So our EDL sequence from entry interface to landing is about 2.5 hours, slightly longer than on Mars. We spend quite a bit of time on the chute.
2.5 hours of terror.
Correct. And there is no sky crane. There is nothing that gets us to a soft landing on the surface other than ourselves. So about 1 kilometer off the ground, we actually cut free from the aeroshell. We go through an event called pose where the lander is lowered, the rotors spin up, we despin the yaw rates with the rotors, and then we pop the separation nuts on the lander and fall. And then from 1,000 meters up, the vehicle flies itself down. We start doing a safe landing site search at about 100 meters AGL. And then when we find the safe landing site, we land for the first time under our own power. So that is a unique flight and can't wait.
Yeah, that's going to be really cool, but also kind of, nerve-wracking. And even if everything goes right in that circumstance, it's going to be on this world for a while. So what happens if something goes wrong during the flight, given this communication delay? Like, what autonomy does the spacecraft have to handle a situation like that?
So we have a very robust fault management approach. As you can imagine, it's about a 90-minute one-way light time. And so, there's nobody behind a joystick, nobody that can take control. And we have a whole team that has been working through fault trees and planning responses to each, and then also testing that both through some of our closed loop sims and some of our planned mission sims with flight hardware in the loop. There's three main categories of responses. The first one is a return to a previously scouted safe landing site. And so that is really used where we see a loss of redundancy, something that says, hey, we're a little bit squeamish about moving forward, but the vehicle can still fly and fly safely. Let's fly back to a safe landing site. Let's call Earth and let's see if we can do some troubleshooting. The second response is a search for a new safe landing site. And so that might be used when we are a little bit perhaps too far from the previous takeoff site. Maybe our battery state of charge doesn't allow us to get back. And so we enter more of a first flight operational contingency where now the vehicle is looking for its own new safe landing site. And as soon as it determines a new safe landing site, it'll land right away and then call home and get ground in the loop to see what's happened. And then the most critical of the three responses is a land now. And so that is triggered when we see something that actively risks the lander. It could be critically low power, low state of charge. It could be a temperature on a component that we see trending very high. And that is a response that basically says, hey, get on the ground now. The vehicle, as it's flying, is looking at breadcrumbs and it is actively looking for safe landing sites. And so at that point, it picks the safest landing site it has and then goes to that. And so there's all sorts of ways, all sorts of testing we're done where, depending on the fault, we have high confidence that we can get back safely on the ground. And testing and simulation here is key.
Yeah. Although difficult to test every single scenario, right? So I'm glad that you're thinking through them and testing them in simulations and doing all these kinds of things because you never know what might happen on another world.
Oh, yeah.
So you mentioned earlier that, we're going to be trying to learn more about what's going on with the organics on this world and what's going on with the ground by, for example, using the LEDs on the Dragon Cam, right? But that's just one way that we can try to analyze what's going on in that world. And there's a lot of complex instruments on board the spacecraft that's going to help us understand this world better. And thankfully, a couple of weeks ago, we did kind of a more in-depth dive into what was going on with testing organics on Mars. So thankfully, we've talked about some of these kinds of instruments like mass spectrometers, but I want to talk a little bit about what's on board Dragonfly and what we can actually learn about this world while we're there. So we'll start with that mass spectrometer, the DRAMS, I think it's called, which is very similar to the SAM instrument on Curiosity. How does that allow you to kind of analyze the organic molecules on Titan without accidentally destroying them?
So the Dragonfly mass spectrometer, or DRAMS, does measurements of very small samples. We have a drill rotary percussive drill that will break up material on the surface. And again, because we have this great cold atmosphere, we can effectively vacuum it into the sample cups in the mass spectrometer. As you say, the DRAMS instrument is based on flight heritage instrumentation from the Curiosity SAM instrument. There's a lot of good understanding of how that instrument has worked on Mars and what we've been able to learn from it. Of course, at Titan, we're in a very different environment with respect to the amount of carbon and the carbon complexity. So we have two different modes. We have the laser desorption mass spectrometry and the gas chromatography. And they function in somewhat different ways to give us different information about the range of materials on the surface, especially at the large molecular scale that we know is present on Titan, to be able to measure, very large molecules. And then also with the gas chromatography capability to look at the structure of those molecules, which gives us important information as well. And so what we want to understand is whether these environments on Titan, where in the distant past, these very complex carbon molecules that have formed in the atmosphere and fallen out onto the surface have had the opportunity to mix with liquid water, to understand how far the chemistry progressed there and whether the processes there actually produced biologically relevant compounds like amino acids, like proteins, the building blocks of what developed into life here on Earth. Because it's very hard to study the prebiotic chemistry here on Earth. Biology overprints everything, which is good for us, but it makes it hard to study those really early steps. And in the laboratory, we don't have the same timescales. And Titan has been doing these kinds of, chemistry experiments for thousands, tens of thousands, hundreds of thousands, maybe millions of years. And so it'll be fascinating to see what has developed, how far that chemistry has progressed.
Yeah, especially with everything we've been learning from both Mars, but also samples that have been returned from asteroids. We're finding all of these really complicated building blocks of what is basically like the beginnings of what could be RNA and DNA on rocks just all over the place. So I can't even imagine what's going on Titan.
And one of the awesome things about our solar system is that we have such a wide variety of planets and moons and asteroids, comets with such different histories. And each of them can give us insight into different aspects, of the formation, evolution of these different types of worlds and the kinds of molecules and chemistry that are possible in these very different environments. It's very exciting.
And even if there isn't liquid water on the surface, I understand there's a lot of frozen water underneath the surface of all these dunes. So who knows what's going on with mixing underneath the ground? I mean, that's some complex stuff that, I cannot wait to see what this thing finds when it gets there.
And that's one of the beauties of being able to fly. That's really one of the advantages that flight gives us, is that we can get into environments on Titan that have very different geologic histories, very different types of chemistry that has occurred in the past, to really understand what has happened in these different areas. The interdunes may have a water ice composition in places that represents the primordial water ice crust of Titan. The dunes themselves have this organic hydrocarbon sand that may be very widely sourced from across Titan. And then, of course, ultimately, Dragonfly will explore the deposits associated with an impact crater where the materials may reflect the chemistry that could occur in the past when we had this opportunity for liquid water to mix with these complex organics. And so we'll have this wide range of different geologic environments and different geologic histories and chemistries.
Another one of the ways that you're going to be testing this material is with an instrument. I just love this name, Dragons. It's the Dragonfly Gamma Ray and Neutron Spectrometer. And my first question, I guess, is what exactly is the physics of firing neutrons at stuff on the ground and then reading the gamma rays? Like, how does that teach us more about this material without actually taking a sample?
Yes, by using this technique, you can measure the bulk elemental composition of materials. Often, gamma ray neutron spectrometers fly on spacecraft, far above planets. We've sent them to a number of planets in the solar system. For Dragonfly, of course, we'll be down on the surface, and we're protected by this dense atmosphere. And so we actually have to bring a neutron source with us, because the atmosphere also protects the surface from the cosmic rays that usually excite the gamma rays and neutrons that the instrument measures. So we actually bring a neutron source, and what the instrument does is look at the energy of the gamma rays and neutrons that come off of materials in the surface as a result of being, of the neutron source, and that the different energy the different elements have different energy signals, and that allows you to understand the elements in the surface materials. So this allows us to characterize the composition of the material. Are we on a organic rich layer? Are we on water ice? Things like that, and that allows us to characterize the material. And in fact, if there's a shallow layer, a thin layer of organic material overlying water ice, say, a few inches deep, we'd actually be able to sense that there's water ice at depth. And so it gives us a little bit of information into the layering right beneath the lander, which will be very interesting as well.
Oh man, I can't wait to see what this thing does, but also it just makes me wish that we could take a whole chemistry lab out there with us, right? But unfortunately, we're limited in what we can do, and that's true on any world until we can get samples back, right? But I did want to ask, because in a previous episode, I had spoken with Amy Williams, who works on the Curiosity team, about how they're testing these samples of materials on Mars. It was specifically about their TMAH experiment, which I won't go into right now, but she said, when I spoke with her, that there was a similar experiment that was going to be on Dragonfly. Is that correct?
Yes. So in the mass spectrometer for the gas chromatography mode, we use a derivatization agent. This is a chemical that reacts with the material and allows it to be volatilized as it's going through the mass spectrometer to measure the specific compositions of the components of the material. So we have a couple of different derivatization agents, one of which is the TMAH. The other one is DMF, DMA, and the MoMA instrument for Mars exploration actually has both of those as well.
This is going to be awesome. We're going to be able to compare all these different worlds, all these different ways of sampling. I cannot wait for it to get there, but we're going to have to wait until 2034 for this thing to actually reach Titan, which is all right. But once we actually get there, I mean, what would be the biggest marker of success to both of you? Like, what is the headline that you're really hoping we can get out of this mission?
It's a mission of exploration. So one of the most exciting things when you're exploring places you haven't spent a lot of time in before is the discoveries that you didn't expect. So I fully expect that there will be things that we're surprised by at Titan. But fundamentally, Dragonfly is a chemistry mission. We really want to understand those early chemical steps and how far organic synthesis can have progressed on an ocean world in the outer solar system that is very cold, but yet in many ways surprisingly Earth-like, especially chemically. And so really to see how far that has progressed in this very different environment. And then what that can tell us possibly about the same kinds of chemistry and the chemical steps that may have occurred here early on Earth. One of the things I really like about the mission is that we get to put that into the context of understanding the Titan environment and really get that bigger picture of aspects of Titan's atmosphere and methane cycle and the geologic processes that are transferring, mixing, modifying materials on the surface, and then the opportunities for those to have mixed in the past, for example, with liquid water at an impact crater or with liquid methane. So I like that we get that kind of full view of Titan as a system, even though we're exploring one small portion of Titan as a world.
From my side, that's the exploration of Titan too, and I love the Cassini-Huygens picture that shows the surface of Titan, because you can almost close your eyes and pretend you're standing there. And so one of the things I'm very much looking forward to is that first picture from Dragonfly on the surface, maybe with a rotor in one of the field of views, because we'll just catch the tips on the side cams. And being able to close your eyes and vicariously be on Titan, maybe not feel the ground beneath your feet, but it becomes a real place that you can explore and visit. And just the expansion of powered flight onto yet another world. I'm a huge fan of Ingenuity. The first flights and what Ingenuity was able to accomplish is mind-blowing to me. And to be able to enable that critical and amazing science that Zibi was talking about through powered flight and discoveries, the exploration that we're going to be able to do on that world, to me is mind-blowing. So can't wait for EDL, can't wait for that first flight, and can't wait for many more flights after that and many discoveries.
One thing I'll add is that we'll be able to do some imaging, some aerial imaging while we're flying. So I think that also is going to be really evocative of, getting to see Titan from that perspective, as well as on the surface. It'll be very, easy to, as Felipe says, to feel like you're in the Titan environment, you're self-exploring.
Do we still have a microphone on the lander, Zibi?
No, there is still a microphone, so we'll be able to listen as well. Although we'll mostly probably hear the lander itself.
Yeah, the fans and the rotors, but the wind gusts and who knows what you're going to hear on Titan. To me, that what I get out of the Mars missions the most is that kind of data set where you can, almost strap on your spacesuit and put yourself in, whether it's pictures or visuals or sounds. And I love that we're going to get enough of that on Titan that, I can't wait to close my eyes and vicariously be on Titan with the lander.
Yeah, sometimes it's like I've spent so much time listening to things from Mars and watching things from Mars. I have these really vivid dreams of what it's like to be a human standing on that world. And I think after Dragonfly is done, I might start having Titan dreams. And I'm waiting for that day. So thank you so much for all the effort that you guys have put into this just amazing mission and for coming on the show to talk with us about it. I know we still have 2 years out from the launch and there's a lot left to do, but you guys have made amazing progress. And I'm so excited about this. So thank you for joining us.
Thanks for having us. It's been a blast.
Thank you. It's been great talking to you.
I cannot wait to see what Dragonfly finds when it finally touches down on Titan in 2034. But while we wait for the first flight on an icy moon, we can look back at the little rotorcraft that proved flying on another world was even possible. Let's turn things over to our chief scientist, Dr. Bruce Betts, for What's Up, and a look back at the legacy of the Ingenuity Mars helicopter. Hey, Bruce.
Hey.
Is that the sound of your rotors spinning?
Yes, it was. It's a Bruce fly.
A Bruce fly. No, really, though. I mean, I know I was just saying this a few weeks ago, but it still trips me out that Dragonfly is literally taller than I am. Like, this thing is so big.
Does that really say that much? I mean,
it's true. I am a little short, but still.
No, it's amazing, and it's a surprisingly big beast compared to what we're used to here in drone land, and it just helps having that low gravity and big, thick atmosphere.
Yeah. It also gives me like a real appreciation of the fact that we've flown on any world at all. Like after talking to Felipe and hearing more about the actual engineering design of the rotors and how they have to think about this world they've never been on, I think about the fact that we flew on Mars and how difficult that's got to be given how thin that atmosphere is, right? The fact that we've done any of this at all is cool.
Yeah, no, it not easy. Not easy. It's amazing that they flew even the little guy, but it did great though. It did our first powered flight on another world. Well, powered, controlled flight.
I did want to ask, so like the reason we use that phrasing, a powered controlled flight, is that because like technically we've launched off of the moon? It's not like we flew around the moon, but we've landed and left another world before. So in this case, it's like a powered controlled flight in that we're staying in the air and zooming around. Is that the case?
There's more. There also were the Vega balloons and the Venus atmosphere in the 1980s from the Soviet Union, partnering a little bit with us. And so they flew, but they were not powered and they were not controlled. But also, we've done, I guess that makes sense. We've done some controlled flights. But the other thing is it's just key. I mean, we use that terminology with the light sail too, because we were doing not powered, but it was solar radiation pressure pushed, but controlled, because the whole point was like with the helicopter, it doesn't do you any good if your helicopter flies, but you don't have any control over it. Well, spacecraft get pushed by solar radiation pressure, but it only really matters if you can control it and use the propulsion. So that's why.
Yeah, that makes sense. Well, since we've been talking about Dragonfly, I figure we should take some time to actually talk about that first powered controlled flight, Ingenuity, which honestly, it feels like just yesterday that little thing like rolled out from underneath Perseverance. Those images were so cute, and I am sad that Ingenuity is no longer helicoptering around there, but we're about to have all kinds of drones. So
it did its little short test flight. It was originally designed, it was kind of stuck on late in the process as an engineering demonstration and was planned for 5 test flights in 30 days. That was their level 1 requirement. But they ended up doing 72 flights over nearly 3 Earth years. And just, what other statistics you got? Its final flight was 2024, flew a total of just over 2 hours, covered about 11 miles, and reached altitudes as high as 24 meters, high altitude for Ingenuity. So it was a wonderful precursor, very much harkening back to Sojourner on Pathfinder as the first little rover that led us to big rovers that did all sorts of stuff later.
just imagine, like, whenever we drop one of these rovers on another world, maybe, I mean, if the conditions are right, if it has at least a tenuous atmosphere, as Mars shows us, maybe we can fly around, like, scout things out. I don't know. I mean, but still, I mean, the fact that we're stepping up from there to something as big as Dragonfly, Titan is very unique, but I was completely impressed by Huygens just dropping a probe onto that world, let alone flying around Titan. Like, it's so cool.
It's very cool, but definitely, huge challenge, much different than Ingenuity. Really easy to fly conceptually, but it has to be fully autonomous. There's no rover to come play with it, and it's 1.5 billion kilometers away, so the light time is, it's an engineering challenging mission, but how awesome will it be if it works? So here's wishing them do it. Wishing them do it.
And that's not the only possible flying missions we're going to have in the future, right? I mean, we haven't talked a lot about this since the Ignition Day episode we did a few months back, but this whole concept of Skyfall and Moonfall Ingenuity-based probes that they're going to be sending out to the Moon and Mars is really interesting. So I'm looking forward to learning more about that.
Yeah, those will be challenging. And I'm still working on the connection between Moonfall on an airless world and Ingenuity, but they both fly around. They just use different techniques. So yeah, if those work, those will be nifty. There's no doubt. We'll move on to
random space fact.
If you squished all the asteroids together, they would still be much smaller than the Earth's moon.
Like just all the asteroids in the asteroid belt?
Take them from wherever you want. But yes, the asteroid belt, and then there's a much smaller quantity kind of inwards and outwards of that. I don't know that we're counting the trillions of objects out in icy land out in the distant solar system, but certainly the asteroid belt gives you, the mass of the asteroid belt is only a few percent the mass of the moon.
I mean, it makes sense. We got a pretty big moon for a world our size, which is
but there's amazing. a bunch of those asteroids.
There are a bunch of them. And next week, we're going to be talking a lot more asteroid stuff, so I'm excited to get into that.
Ooh, fun. All right, everybody, go out there, look up the night sky, and think about twinkly lights. Thank you, and good night.
We've reached the end of this week's episode of Planetary Radio, but we'll be back next week with more space science and exploration. If you love the show, you can get Planetary Radio t-shirts at planetary.org/shop, along with lots of other cool spacey merchandise. Help others discover the passion, beauty, and joy of space science and exploration by leaving a review and a rating on platforms like Apple Podcasts and Spotify. Your feedback not only brightens our day, but helps other curious minds find their place in space through Planetary Radio. You can also send us your space thoughts, questions, and poetry at our email at planetaryradio@planetary.org. Or if you're a Planetary Society member, leave a comment in the Planetary Radio space in our online member community. Planetary Radio is produced by the Planetary Society in Pasadena, California, and is made possible by our members, who cannot wait to watch another rotorcraft take flight in the skies of an alien world. You can join our global community of space enthusiasts at planetary.org/join. Mark Hilverda and Ray Paoletta are our associate producers. Casey Dreyer is the host of our monthly Space Policy Edition, and Matt Kaplan hosts our monthly Book Club Edition. Andrew Lucas is our audio editor. Josh Doyle composed our theme, which is arranged and performed by Peter Schlosser. My name is Sarah Al-Ahmed, the host and producer of Planetary Radio, and until next week, Ad Astra.